Okay, I guess we'll move forward. Again, starting off, low-level detection of ammonia, new method validated following EPA guidance, ATP case number N08-0004. If for some reason you can't hear me, please just type in down where it's chat saying can't hear you. Okay. So, again, new method ATP language. This is in the ATP letter. It says it is recommended that this method be included in future regulatory actions and adds to the list of approved methods in 40 CFR 136. However, this ATP review does not replace this notice and comment rulemaking process. In the interim, though, a user may, on a facility-by-facility basis, seek approval from their regional authority for the use of this method in measuring ammonia in Clean Water Act programs. So what does that mean for the laboratory? First thing you have to do if you wish to use this method for Clean Water Act, you need to contact your state and regional coordinators, in plural there, if your lab is doing work in more than one EPA region. So you need to do that. And the state in the case is if the state has some regulatory authority on this or if they interact with the EPA regional ATP coordinator. So I would suggest you do both. You reference the ATP case number N08-0004 when you talk about this so they know exactly what method you're talking about. You ask for approval to use this ATP for Clean Water Act testing, for ammonia and ammonia determination of TKN digestant. So that means after you digest the TKN, you can use this to determine the ammonia concentration in this digestant. Now, here's the note. Here's where we broke off when my audio went bad. But for Safe Drinking Water Act testing, there is no ammonia method listed in 40 CFR 141. But there are drinking water laboratories that have to do ammonia testing, either due to the fact they are making chloramines or the fact that they have a natural source of ammonia from plant matter decay coming in specifically in a surface water plant. Again, even though it's not in 141, you do need to contact your state and EPA drinking water contacts. And that could be the ATP people. It can also be whoever's doing laboratory certification for your drinking water laboratory to see if it's approved to use this ATP. So don't just assume that it's not in 141 that you can just use the ATP. 141 says you may use other methods that are approved by EPA. But since this is a recommended ATP, not approved at this time because it hasn't gone through the promulgation process, the comment and review period and such for formal promulgation, you still have to contact your regional authorities and for the Drinking Water Act, your drinking water certification people also. So let's take a look at the type of ammonia detection that's out there. And we basically have, and let me grab a highlighter. All right. We seem to have lost something here. Okay, let's go back one. All right, we'll just stick with just the arrow. We have the typical titration with sulfuric acid, an endpoint going from green to lavender. It's a mixed reagent, a mixed indicator, methylene blue and methyl red. So you go from a green color to a lavender color at the end of it. You have the ion selective electrode that allows ammonia to permeate through the membrane, and you basically have a pH change inside the electrode. You have the phenate reaction, perflux reaction, in which you react with ammonia and you form a photomer here that has a certain color. It does change with time. You also have the Nessler's reaction, classical with mercury. You get an orange-brown suspension, which will settle out with time. And now we have the membrane extraction. And basically what you have is your sample is made caustic with sodium hydroxide. It permeates the membrane. It's picked up by a boric acid buffer. And then this change in the boric acid buffer you measure as a change in conductance. So let's take a look at, do I need to do distillation? Can you hear me now? Sarah?
Yes.
Did you lose me there again?
I think we did for just a second.
Just for a brief minute.
Okay. Where did you lose me?
Just at the beginning of this slide.
Okay, at the beginning of this slide. All righty. So let's take a look at the detection method. And is distillation usually needed? For titration, yes. Is that there's very few cases that you don't do distillation prior to doing the titration. The same with the Nestler, and specifically with the Nestler, since you're measuring a suspension, a finely divided mercury suspension there, that any type of solids in your sample can lead to a false positive. The ion selective electrode, maybe, maybe not. There are laboratories on their final effluent from a wastewater plant that have done comparison studies where they show, yes, we get the same number whether it's distilled or not. They're allowed to do that. But if there is any interferences, you really want to distill. Same way with the phenate method, because what you're looking at is a color change, but also if there is suspended material in the sample, that will actually scatter the light and you'll get a false positive. It'll come off as absorbance, but it really isn't. It's just light scattering. The ATP, the membrane extraction conductance, no. The distillation, we actually did the analysis where we did not distill before, and our matrices showed that we did not seem to have a requirement to distill. Now, there's always a caveat on that. If you have an extremely heavy and thick and full of solids sample, you may want to distill. But we did things on final influent, some of the nastiest sample you can have, and we had no problem with that. Or excuse me, not final influent, raw influent coming into the wastewater plant. So full of solids, what you expect to come into a wastewater plant, and we had no problem with that. Okay, here's the Timberline, just a picture of the most current instrument, and basically a schematic, and where you have the sample, the caustic solution, the absorber solution. It's pumped with a peristaltic pump. It goes through the hydrophobic membrane, the gas diffusion cell. The ammonia comes out of the caustic. It diffuses through and goes to the conductivity cell. Okay, what did we use for this ATP? First off, number one, the protocol for EPA approval of new methods for organic and inorganic analytes in wastewater and drinking water. We followed that to the letter, that EPA guidance. The next one down, we also utilized the Youten pair test from the standard practices for the determination of precision and bias and applicable test methods of the Committee of D19 on water. So that's ASTM D2777-06. We also utilized standard methods for some of the classical percent recovery. So standard methods for the examination of water and wastewater, Part 1000 and Part 4000, because ammonia falls under Chapter or Part 4000. Here are some of the EPA calculations we utilized. Okay, Sarah, am I still on?
Yes, you are.
Yes, okay, good. Now I'm getting paranoid. All right, and this is from the EPA guidance. We used a pooled MDL. We utilized the pooled relative percent standard deviations, and actually what was the RSD cal max, and we looked at our RSDs compared to that. We utilized the maximum, calibration verification calculation. We used initial precision and recovery, including what is acceptable upper and lower limits. We used ongoing precision and recovery, here in yellow, including what is the acceptable upper and lower limits. And we used the matrix spike and matrix spike duplicate acceptable recoveries calculated out. Other calculations, just to let you know, there's the mean, relative percent difference. percent recovery for the LFB, percent recovery for the LFM and LFMD. The outlier test. We did outlier analysis on one data point and all of the data collected. And it was due to a bubble formation in the detector. The outlier analysis allowed us to discard one data point out of everything. So we used all the other data, warts and all, in the sense of wanted a very robust method. And then down here is the ASTM calculations, and that is for the single operator standard deviation. So let's take a look at some data. Okay, and here is a standard calibration curve. We did a calibration as quadratic because there is a slight curve to it. It also allowed us to expand the dynamic range we were working in. So typically a blank 1, 2, 3, 4, and 5 calibration points. Okay, method detection limit. This is calculated as per the pooled EPA requirements. And Sarah, can you still hear me?
Yes, we can.
Okay. All righty. So here we have the total laboratory MDL. Very good. This is for a 4-inch membrane. So now we're talking roughly 15 ppb. Here is the minimum level. And here is the corrected reporting minimum level as required by the EPA guidance. We have to round it to the nearest fraction or percentage of 1, 100, or 5, or 50, or things such as that. We also did a 10-inch membrane. Now, what you get with a 10-inch membrane is you get a lower method detection and ML, minimum level. You get a lower one of those. And it does not have as high end of the dynamic range because you get a lot of signal. And the only difference between the 4-inch membrane and the 10-inch membrane is the length of the membrane. So you used to have more extracting capability with a 10-inch membrane. So very, very low concentrations you go with a 10-inch. The rest of the range you stick with a 4-inch. And so here we have basically the MDL 3, the ML of just under 9.5, and a reporting limit of, or a reporting ML of 10 ppb. So very, very robust MDLs and MLs. LFBs, average recovery. Well, you'd want the LFB to be very good. You're doing that in DI water. You're spiking it with a known amount concentration. We had them spike it at the middle to the lower 10% of their calibration ranges, so we didn't overload the LFB to always pass. And we had very, very good recoveries. Lowest is what, about 88%, 87.5%. The highest, 103, 104%. And the average of all of those, just a little bit above 95% for the LFB. The 10-inch LFB, again, much smaller concentration. We've got a very good recovery, 95% to roughly 97.6%, averaged out to 96%. So again, very good recoveries on the LFBs. Now, the matrices. Since we're going to be using this in wastewater, this is key to see how robust this instrument is. So I started off when I was talking about we had raw POTW influent. That's basically with everything coming out of the sewer. At the front end of the plant, here's the sample. This is even before the grit chamber. This is the raw material. We have primary clarifier effluent. So this is basically after the primary clarifier where you try to settle out most of your organics, like, you know, the heavy stuff you find in sewage. And this is a mixture of light organics and whatever else is floating through. Return waste activated sludge centrifugation liquor. So this is a plant that has to remove ammonia. So they centrifuge their activated sludge, basically their biomass. They centrifuge it, and that centrifugate has a lot of dissolved material in it and it has a lot of ammonia. So this is a high ammonia concentration sample. The POTW effluent, so basically after everything is treated, before it's chlorinated. So this is pre-disinfection, okay? The POTW effluent dechlorinated. So they dechlorinated by sodium sulfite. So they added a sulfur compound to remove excess chlorine. So they disinfected with chlorine, then they removed the residual chlorine to meet their discharge requirement. The receiving watershed for the POTW. Okay. Then we had 3 different categorical effluents. And this is an in-depth discussion with EPA before we started this. This is an approval of these matrices before the first data point was collected. What we looked at are industrial effluents. So this is basically indirect dischargers. They are discharging to the sanitary sewer, but this is coming out of their facility. So it's going to go down the sanitary sewer. So it can have all the solids in it at once and everything else. It'll be treated by the wastewater plant. So this is fairly aggressive material. So we have a metal finisher. That's 40 CFR 433. That's a categorical one. We have a commercial truck wash, which basically it's a facility that cleans out the inside of tankers, so you don't know what they're cleaning out, except it can't be, RCRA waste and such. But any type of material, and it has a lot of detergents in it and such, something that will challenge the extraction membrane. And then a pulp and paper mill. This was a direct request to try this on a pulp and paper mill waste. And then we actually had a Keldol digestant, and it came from a wastewater lagoon that handled a lot of liquefied manure. So pretty good sample there. So those are the type of matrices we looked at. You're supposed to look at a minimum of 9 matrices. We looked at 10. Next slide. So can you still hear me, Sarah?
Yes, we can.
Okay. All righty. So let's look at the matrix spike and the matrix spike duplicate recoveries. This is important because if you're not going to distill, you would like to see, can I spike it and get it back, knowing my initial ammonia concentration. If I'm not going to get it back, then I'm going to have to worry about distilling. Now, here's the interesting thing. You can see we're going from 80% to 140%. Commercial truck wash. We did get a high recovery on that. Raw POTW influent. You notice there's a big difference between the two of these. And that's to be expected because the influent has a lot of solids in it. It's not a homogeneous sample. So when you spike that, you would expect to see some variation. The final POTW effluent, dechlorinated, this has the sodium sulfite in it. So there might be a problem with this. This might be something that if you see matrix recovery that does not meet the method, then you may have to distill. Okay. Everything else looks very good. We have nice agreement between them. And if we just look at the average, we have 105 to a little bit over 112%. So 100, maybe that's what, 107 to 112% recovery of the LFM, LFMD 4-inch membrane. If we look at the calculations from the EPA statistics, it says all laboratory MSD lower limits 83.99%, so this is from all the data. The upper end 135.32%. Now, when this method was finally written, basically in discussions with Len Walker and Kevin, we decided that even though we have a little more excess up here, we're actually going to trim that back and make it a tighter limit. 4-inch LFM, LFM RPDs, very good RPDs down here with everything agrees with each other. And again, as we talked about the commercial truck wash, but it's still below 10%. The raw POTW influent, it's below 20%. There's that one, that dechlorinated that pops way up there. So that's one of those samples that you may want to consider. But here's the thing. If your matrix spike and your matrix spike duplicate meet the requirements of the method, the QC requirements of the method, then you don't have to worry about this one. But again, in developing this method, we do have some outliers. We did not get rid of any of the warts. All this has been put together, warts and all. It's a very robust method. And we'll just jump ahead here. LFM, LFMD recoveries, 10-inch membrane. Okay, again, you would expect this very, very homogeneous. There's the receiving watershed. There's a metal finisher effluent. Metal finishers are watched so carefully. They're really careful about what they discharge down the sewer. And there's PODW effluent, non-disinfected. So it just seems the sulfite might be a problem. And again, here we have from the EPA calculations, 87.67, lower limit 114.57, upper limit. RPD, that looks very nice. Everything below 10% for the 10-inch membrane. Now let's talk about the Yowden pair. The Yowden pair was a group of blind checks, single blinds, sent out to the different laboratories. You can see the percentage of recovery. There's 100%, there's 120, but look at that. That is really good across there. Single analyst percent RSD, single analyst standard deviation, very good. Percent RSD, very low on this. Yowden 1, Yowden 2, and Yowden 3. So there are different pairs, and each lab got 2 different sets of blind checks. Here's Yowden pair recovery, and this is the ASTM Yowden pair recovery, single analyst, precision and bias. Sure enough, here's the percent RSD, standard deviation, very good. Percent RSD, 0.06%, very good for that. And the percent recoveries you can see, very respective. All right, so let's talk about the method now. So here's the thing, 40 CFR part 136.7. What's in that section was in the memo Dick Redding wrote in 2007. So it's not new. We just made sure that this is in this new method, that we meet all the requirements here except for number 6. We don't have any internal standards or any surrogate standards or tracers. So everything else was met in the method. And let's take a look at a little bit of it. In the method, we talk about initial demonstration of capability. All right. So IDC control limits for the laboratory is based on the limits determined in this method. So that's initial precision and recovery in the method, and shall not exceed 82% to 110% with a percent relative standard deviation of less than 8%. So we took the limits that were developed in this method, initial precision and recovery, put it in this method, and in some cases, if it was reviewed by Lem and Kevin, and we say, look, we'd like to have it just a bit tighter. We looked at things, we said, yes, that's reasonable. But we talk about initial demonstration of capability as a laboratory fortified blank whose concentration is between 10% and 50% of the dynamic range is analyzed 4 times. The mean recovery and the standard deviations are calculated and evaluated for acceptance. What we've also added in this method is the new procedure of saying if it doesn't fail, or if it does fail, what do you do? And we say down here, and this is what we've done in multiple points in this method for each of these types of QC, and it's specifically meeting those points in 136.7. It says if the IDC recovery falls outside these limits, the analyst or instrument is judged to be out of control. Bingo, right there. If it's outside of this, the analysis is out of control. A root cause analysis must be performed, corrective action taken, all findings recorded, and the IDC repeated until passed. Laboratory reagent blank, we actually have, again, the same thing. What is the acceptance criteria? The LRB concentration results will be below the lowest calibration standard in the dynamic range. And we say if the LRB falls outside of the acceptance limits, again, the batch is judged to be out of control. You have to do a root cause analysis, corrective action taken, all findings recorded, and the sample batch repeated. So for the laboratory QC auditor, they have control now over what's done if something happens. For the auditor or inspector that comes in to look at things, they actually know for this method, if you're using this method, you're going to have the following for me to be able to review, including if you have something that's out of control, what is the corrective action taken, what is the root cause analysis completions, where are your findings, and show me that you repeated the batch. Again, laboratory fortified blanks. We'll just go on to the next one. LFM, LFMD. Now, people may say, why is that 84 to 115%? We looked at the LFM and LFMD recovery calculations from the EPA formulas there in the guidance, and we decided that we'd rather have these just a bit tighter than some of the loose ends on it. And that's not to say the LFM and LFMD work done is not accurate, but this is basically, again, saying we want to make sure we have really tight, these are very achievable with the instrument. We see no problem with that. If you fall outside of this, though, the 84 to 115% recovery and RPT shall not exceed 20%, if you fall outside of that, then you are basically, is judged to be out of control. Ongoing demonstration of capability. We're allowing you to set control charts on ODC. Your IDC is a calculation, and you get a RSD, you get a percent or an average recovery, all right? Your ongoing demonstration of capability, your LFB as you're running each batch has to fall within the control chart limits, okay? So that gives some flexibility to the laboratory and to the auditor on how to look at this ongoing demonstration of capability. But again, if you set up your control charts and you fall outside of those, you're still to be judged to be out of control. A root cause analysis must be performed and corrective action taken. We also added in the method is, what is an analysis sequence? Okay. Now, it doesn't say you have to do it this way, but we say a typical sample analysis sequence. Well, instrument startup. Well, that makes sense. You cal the instrument, you cal zero it, you run your calibration standards 1 through 5. So your 0 is not a calibration standard. When you zero the instrument, that's not a calibration standard. You run your calibration standards, you're a 5. You then basically calibrate the instrument. You run your LRB. If your LRB fails, then you don't need to go any further, okay? You run your LFB. If your LFB fails, you don't need to go any further, okay? Then you say, okay, I'm going to run my sample that I use for my LFM and my LFMD. Then I run my LFM and my LFMD. If it fails, you don't need to go any further. Then you run your first half of your batch, and we've defined a batch as 20 samples. So first half of a batch you run. Then you run your continuing calibration verification. If it fails, you don't run any further. You don't go any further. On the other hand, if it passes, then you do your next set, second half of the batch, and then we say you can repeat the CCV as optional at the end. So when the auditor or the laboratory QC person or the person running the laboratory training their staff, utilizing this method and this instrument, we've helped them at least say there's no question about what a batch is, and there's no question where the QC should be showing up, because there's no use running a batch down here if your QC fails or your calibration fails. Okay? Can you still hear me, Sarah?
Yes.
Okay. And then we talk about initial calibration. In that, we say a linear or nonlinear correlation coefficient for the standard concentration to instrument response shall be greater than or equal to 0.995. We recommend in this that you do a polynomial curve fit. But again, a linear curve fit is actually a polynomial curve fit with very strict requirements to it. So if you want to do linear, we do have that up here as an option, but again, you have to meet this requirement. We also have standard back calculations. And in that, we say you back calculate your standard concentrations from the calibration equation. And the concentrations that you come up with should agree within plus or minus 10% and cannot exceed plus or minus 15% of what you calibrated to. So an example, let's say you're using a 10 ppm standard. You run your calibration line. Then you go back and recalculate that standard from the calibration equation, and it's got to agree at least plus or minus 10% or cannot exceed plus or minus 15%. So if I have a 10 ppm standard, plus or minus 10% is 9 to 11, or 8.5 to 11.5. So you've got that situation there that you go back and you check your calibration line, because no matter if it fits well or not, it's got to be able to calculate standards. And really this catches at the high end or the low end of your calibration, whether you have something where maybe you have too big of a dynamic range. Maybe you should narrow it up because your calibration line just doesn't fit well at the low or high end of your calibration standards. Continuing calibration verification, again, we have cannot exceed 90 to 110%. So even if we look at the back calculation there, we've tightened it up on the CCV. Now we're getting down to the end here, the root cause analysis. So what are we going to do with that? Well, we just define it, and this comes from ISO language. It says corrective action, root cause analysis. A laboratory analyst and laboratory management will perform a root cause analysis for any QC failures. The analysis will have at a minimum the following areas described in detail. You identify the problem, investigate to identify root cause, come up with a solution. Rerunning the analysis is not coming up with a solution. Implement the solution so you don't have a repeat on this. Document the solution. Communicate the solution. Develop training and management programs to communicate and evaluate all personnel included in the corrective action solution. And then evaluate the effectiveness of the solution. So just rerunning the analysis, at least in this method, is not just the root cause analysis. So you have to perform a root cause analysis if it fails. A QC step fails, which is good anyway, because number one, you correct it so it doesn't happen again. You validate your data for robustness. You validate the method for robustness. You validate the training and your personnel for robust behavior. And you can show that to your auditor when they come in. So we've reached the end of this webinar. If you have any questions, please contact Sarah Burry at awtimber@t-line.com for further information on the Timberline method or on this webinar. She has been recording it. If you wish to have this file of this, please contact Sarah. Any other information on this, please contact Sarah if you have any questions. So at this point, any questions? And if your audio doesn't seem to be working, just type in down in the chat line. Can you still hear me, Sarah?
Yes, we can.
Okay, good.
Case of case, just okay.
Okay, so we do have one question here. It says for the Cal standards back calculation limits, you specified two limits, plus or minus 10% and plus or minus 15%. Which limits should a lab use in their QC?
I would say the best is plus or minus 10%. It cannot exceed plus or minus 15%. So that's kind of like your warning limits and your control limits on your DMR QA or your PT samples. Plus or minus 10% is very good, but let's take a look at this. If I had, let's say I'm doing from 0.1 to 10 ppm. So plus or minus 10% on 10 ppm is my final standard. Well, you should be able to make that. But you're down at 0.1. Plus or minus 10% on 0.1, it may be maybe plus or minus 12%. Small changes in a small number can give you a very large percentage. That's the reason why we have that additional plus or minus 15% in there. And that I basically swiped from standard methods QA/QC because we've had people ask us the same question, which one should I use? And if you make it too tight and they're doing very, very small concentrations at the bottom of their calibration standards, they have trouble with the plus or minus 10%. So when we put it in there, it was not to exceed plus or minus 15%, but it's much better plus or minus 10%. So it's like your warning limits and your control limits on your PT sample. Does that help?
Yes, thank you. Any other questions before we conclude the webinar? Well, thank you very much to Ed Askew for giving the presentation on our method, and thank you all for your interest and for attending. And if you have any additional questions at a later time, feel free to contact us at Timberline.